Hello everyone, my name is Aryaz Eghbali and I want to present the work that we have been doing at the SoftwareLab in University of Stuttgart with Michael Pradel. It's called CrystalBLEU, which is a metric for measuring the similarity of code. So assume that I have created a code generating model and I want to evaluate it on some references which serve as ground truth. And my supervisor, Michael, has some coding assignment submissions from students, and he wants to detect some plagiarism or find the similarity between these submissions. So after some search, we find this metric called BLEU, which is a metric for measuring the similarity of text, designed for machine translation evaluation. But it has been used extensively for code during the past few years. So how does this BLEU score work? It's based on n-gram matches. N-grams are a sequence of tokens of length n. And for example, here we have closing parentheses and open curly brackets, which is a 2-gram. And we have open parentheses, close parentheses, and a semicolon, which is a 4-gram. And some of the matched n-grams you can see here are highlighted with the same color. And next, it tries to count how many n-grams are matched. One is the regular count you can see here, and the other one is the clipped count, which is the minimum number of these n-grams appearing in the reference and the hypothesis. So for example, this while open bracket appears in the reference once and in hypothesis 0 times. So the clipped count would be 0, but for hypothesis 2 it also appears once, so the clipped count would be 1. And after calculating these counts, we divide the sum over all n-grams for of length n for the clipped count divided by the regular count, and this would be the modified precision. Then these modified precisions are averaged with some weights, and then there's also a brevity penalty added to this sum. And this brevity penalty is supposed to reduce the score for longer predictions that get a higher precision. This is a very fast metric, and it works for code that is incomplete or syntactically incorrect. It is also language agnostic, but there are some cases that you find similar looking code that are actually different, getting higher score than code that are actually the same. So in this case, reference hypothesis 1 and the reference are the same but get a lower score. Hypothesis 2 and the reference are totally different codes but get a higher score. So we want to mitigate this problem. But why does this problem appear at all? So there are some inherent differences between programming languages and natural languages. And in this case, I want to talk about the strict syntax and some coding conventions that are in programming languages. And these cause some n-grams to be common amongst different programs. And we call these n-grams that appear only because of the syntax, grammar, or coding conventions, or some popular APIs that are used, the trivially shared n-grams. So as you can see in this chart, we have the most common, the most frequent n-grams in a programming language like Java here at the top, and the most frequent n-grams in the English language, which is a natural language, at the bottom. And you can see that the frequency of the n-grams for Java are higher than the frequency for the English language. And this means that we should expect to see more shared n-grams between two pieces of Java programs rather than two pieces of text in English. And that's what we see in this graph. And we calculated the ratio of shared n-grams between two random pieces of text in these languages. And as you can see, the English and French are pretty similar with a low ratio of shared n-grams, but languages like Python, Java, and C have a higher ratio of shared n-grams in random pairs of programs. So how do we mitigate this problem is basically our approach CrystalBLEU. And what we do is we extract these common n-grams, so as the trivially shared n-grams, and then we run the BLEU algorithm, but when we want to count the occurrences of these n-grams, we ignore the top k most common n-grams. And this is very similar to how stop words are used in the NLP field. And to give you an overview, so first we have a code corpus. We take a sample of it and then calculate the trivially shared n-grams. And then each time that we have some references and hypotheses and we want to calculate similarity, we calculate BLEU but ignore these trivially shared n-grams. So to measure how well our new metric performs, we need a meta metric, and we call it distinguishability. This metric measures how well a metric can distinguish similar and dissimilar pairs of programs. So we have similarity within classes of equivalent code and similarity between classes of equivalent code. And the ratio of the similarity within classes to the similarity between classes is this metametric distinguishability. So a metric that has higher distinguishability is better. So we want to answer these three questions in this talk. How well CrystalBLEU distinguishes similar and dissimilar programs, can it avoid misleading comparisons, and how efficient is running CrystalBLEU. So first, the distinguishability. For that, we need some classes of equivalent code, and for that reason, we take the data from ShareCode, which is an online judge. On this online judge, people submit programs that solve a programming task, and the online judge runs these submissions against some test cases. If the code passes all test cases, it's accepted for that problem. And because of this testing framework, we assume that the programs that are accepted for a problem are actually equivalent semantically. And we calculate distinguishability for three different similarity metrics. One is BLEU, the other one is CodeBLEU, which was designed specifically for code, and our approach CrystalBLEU. And as you can see, CrystalBLEU can distinguish way better than the other two. To show it in a different context, we also did a simple clone detection classification. This is not supposed to beat the state of the art, but it's to show how well CrystalBLEU can differentiate similar and dissimilar codes. And we run this experiment on the big clone bench dataset, and we implement this simple threshold-based classification. So we get the score for the average score for the clones, and we get the average score for non-clones, and the mean of these two values would be our threshold. So more similar code would be flagged as a clone, and the smaller values would be not clone. And as you can see, CrystalBLEU can get higher accuracy, precision, and F1 score. And you can also see that there's a smaller overlap between the values for CrystalBLEU rather than blue. So the next thing we want to discuss is can it avoid these misleading comparisons? And for that, we want to look at the task of comparing two models that generate code. In this case, we have a neural model called Concode, and we have a dummy model. This dummy model generates code mostly consisting of common n-grams. And as you can see in these random examples, they look really unnatural and not similar to the ground truth. However, the BLEU score cannot differentiate between these two models, but CrystalBLEU gives a higher score for the neural model rather than the dummy model. And for the example that I showed earlier, CrystalBLEU gives a lower score for the dissimilar pair and a higher score for the similar pair. In terms of runtime, we have two phases. So the first phase, which is pre-processing and needs to happen only once for a particular code corpus or domain. We can see here that for a large data set of almost 3 million tokens, it runs under 30 seconds. And this is including tokenization. If it's already tokenized, it can be done in under 5 seconds. And for the runtime of the actual metric, you can see here that the runtimes are very similar to BLEU, but way lower than the CodeBLEU runtime. So how you can use CrystalBLEU, you can install it with pip, and then you just need to extract the trivially shared n-grams from a tokenized corpus, and then the API for the metric itself is very similar to the implementation of BLEU score on NLTK package. We add a new parameter which you can pass the trivially shared n-grams. So as we have seen, CrystalBLEU is as fast as BLEU and faster than CodeBLEU and some other metrics designed for code. It works on partial code and syntactically incorrect code, and it's language agnostic as long as you have a tokenizer that can tokenize the text. You can apply CrystalBLEU, and it has higher distinguishability. So thank you all for your attention, and I encourage you all to take a look at the code and feel free to ask any questions.